So our next presenter is Patricia. I can say the name properly because she is from a Latin American country, Patricia González Guerrero, from Lawrence Berkeley National Lab. I'm convinced that this will be a very interesting presentation and also align with the program that I tried to put together today regarding hardware and stuff. So no pressure, but just whenever you're right.
Okay, so the title of this talk is Chiplets, a key ingredient for specialization in HPC. So Nicolas asked us to say something about us that is not in LinkedIn. So in the lab, they asked us to do this, and I thought it's a good idea to reuse that. So they asked us, what is your favorite thing about LBL? And everyone said the view. If you have been in LBL, you know that the view there is amazing. But then I love also the leftover food, and that's a testament that Pavlov conditioning works after being a graduate student. I get excited about leftover food still. While I was doing previously, I was traveling around the world. I finished my PhD, and it's like, oh, I want to see the world. I'm done with research. So I went traveling, and then COVID happened, and I had nothing to do. So I was like, okay, let's go back to work. What technical skill I think is something that I should have learned earlier. That's everything's gonna be all right from Bob Marley. And then what inspired me to choose what I do? I'm basically a circuit designer. And it's because I wanted to understand the brain, but at that time I didn't know neuroscience was a thing, so I ended up doing computers. Now I know better; they are different, but it's getting there. And what do I do in my free time? That's something that I found super confusing because I was like, don't remember what is the concept of free time. I'm usually, when I'm not working, I'm being the butler, Alfred, or I'm being Gordon for a 4-year-old Batman that is very committed to the role. So when I'm not chasing villains around with Batman, I'm doing these are the projects I am involved right now. So I'm modeling HPC with FPGAs. I work in specialization with chiplets, something that the previous speaker talked about. I work in superconducting digital computing, cryogenic sensors, and also cryogenic quantum control. My passion is non-conventional computing paradigms. That's why I'm all over the place doing all the things. I also have projects in neuromorphic computing, and recently I'm starting to work in scientific sensors. So if you guys want to talk about any of these, I'd be happy to talk. Why we're doing all this? Why do we have to look into all these topics? So the big motivation for this is that HPC performance does not increase anymore. We were used that HPC was improving by 1,000 times every few years, and that's what we assumed was going to happen, driven by scaling the transistor. But then there are many. It's not only scaling. It's not only more. There are many things that kind of hinder that scaling. We have to talk about the power wall, the memory wall, the I/O doesn't scale at the same level as the transistors. The reason why we're looking into all these beyond more technologies is because we need to answer the question: how do we get HPC performance back on track? And then, a couple of months ago, I had to add the second slide, and is that we are getting into an energy crisis driven by artificial intelligence. We see that data centers are kind of popping up everywhere, and the projections for energy consumption is off the charts. And I was always talking about 25 to 30 megawatts that data centers, but today the speaker talked about gigawatts AI factories. So we are definitely getting into an energy crisis if we don't do anything. Luckily for us, we are scientists. So one of the solutions that came up for the performance issue is, well, we need more transistors, right? So we make larger dies. The problem with making larger dies, like larger chips, is that yield kind of goes it gets really, really bad. So here I'm showing you two toy example of how yield works. So if I have here a very small, if I have very small chiplets, and then I have a density I have these 5 examples of errors in my chip, I get 17 good dies. That's 77% yield. But if I make my chips larger, what happens is that if I have exactly the same error density, I only get 2 good dies. And then my yield goes 40%, and that goes to 40%. And that's kind of one of the reasons why the NVIDIA chips are so expensive, because they are humongous. And then their yield is really, really low. So they don't have as many chips. And then there are other, I'm gonna say, Cerebras also has to deal with this problem if you want to do a wafer scale product. The other option, instead of going bigger, you can do advanced packaging. And advanced packaging is basically that so you can do interesting things with packaging inside the package of the chip. So here I'm showing you an example of early monolithic packaging, when we had just one single chip connected to the PCB, and then we would put together in a PCB, we would put together a couple of chips. The problem with that is that it has a lot of power, because I/O consumes a lot of power. And then it's slow, you have a limited bandwidth. But then as we increase the technology for packaging, we go into the last step, 2.5D, where we have a silicon interposer. And that we can do is use these little chiplets that have better yield, and then we can connect them together very close to each other, and then with very large, a lot of data lanes available for communication. So that means that we have high bandwidth and lower cost in the power consumption. So then this is the other option. So when you go to a conference that is talking about chiplets, people are telling you, yeah, chiplets is the future, chiplets is the future. We all have to move towards chiplets. And what I want to tell you is that that's not true. Chiplets is not the future. Chiplets is the past, is what's happening right now. So when you look about the chiplets, basically they made the exascale possible. You see the 3 top computers in the world, El Capitan, the top HPC computers in the world, El Capitan, Aurora, and Frontier. They are all built on chipletized architectures, Intel and AMD. So it's not the future; it's happening right now. The reason for this is we talk about yield and cost efficiency, but there are also other things. So what chiplets helped us with is we overcome the memory wall. Around 2019, everyone was talking about the memory wall, and then suddenly we can integrate on the same package HBM, high bandwidth memory, and then the chiplet, and they are all in the same package, dramatically increasing the bandwidth between these 2 elements, so that we don't talk that much about the memory wall anymore. It also helped us with heterogeneous integration. So we heard the speakers talking about heterogeneous integration before, and what it allows you is to connect the CPU and the GPU within the same package, again, sharing memory. And even though the GPU is still a general purpose architecture, that is very different from what we have for a CPU. And then it enabled us also to have scalability and modularity. So AMD has a couple of examples of this, where they have the same chiplets, but they vary the number of chiplets that they put in there to give you 2 different products. So if chiplets is not the next thing, what is the next thing? So I'm going to advocate here, and I think that's also something that the previous speaker said, is a specialization. So the next step is not chiplets. Chiplets is already there. Is how do we use chiplets to enable specialization? So hyperscalers are already using specialization in several ways, in several points. But then we care about, like in the lab, we care about the scientific computing. and now artificial intelligence, of course. But then here I'm giving you some examples of specialized units to do scientific computing. The most famous is the tensor processing units for matrix multiplication from Google. The other one that is also a very good example of specialization is the Anton machine for molecular dynamics. And this is very important for scientific computing because it has the potential to 100 to 1,000 more performance, but also 100 to 1,000 less energy consumption, the both things that we care about, the motivation for our work. Why we're not doing this? The big challenge is over specialization. So algorithms evolve faster than hardware, and one example of this is the recurrent neural network. So if at some point where we were seeing the evolution of machine learning, recurrent neural networks was the last thing, you know? So what would have happened if Google, instead of doing the TPU, had spent 100 engineers a couple of years designing a hardware that is specialized for RNNs? By the time the product gets to market, RNNs are already a niche application. There is no market for it, and that's kind of one of the big challenge for thinking about the specialization in HPC, AI, and scientific applications. Okay, so the question I'm gonna keep talking about for the remaining of the talk is how do we leverage chiplets modularity? So hardware specialization makes it into our HPC clusters. We have a couple of products that we have been using that have enabled us to think about this question. We had a collaboration with AMD where we were thinking, density functional theory makes up for 25% of our workload in Berkeley National Lab. So what do we need to do? If we build our accelerator, what do we need to do to put this accelerator in the AMD machine, in the AMD chipletized architecture? And it sounds easy, but it's really challenging because we don't want to know all the secret sauce that AMD uses to build their platform. We don't want to know it, and they don't want to share it with us. So how do you do that? How do you put this chiplet accelerator in this architecture with no knowledge of what's going on within the chipletized architecture? The other interesting project we have is VIAS, is vertically integrated artificial intelligence for sensing and high-performance computing. So a couple of institutions got together, and we are designing 18 different chiplets. And with these 18 different chiplets, we're going to build a vertically integrated system where we're going to have chiplets on top of each other. So first, we're going to have a photonic interface for very fast communication links. On top of it, we're going to have artificial intelligence hardware, which is going to be targeting HPC applications, but also scientific sensing applications. On top of this, we're going to have all the analog part of the sensor, in the case of the sensor chiplets, where we have ADCs, filtering, analog conditioning, and then on top of that, we're going to have the sensor, the scientific sensor. We're working with Fermilabs and others in this project. And then the other project we have is as part of the Open Compute project, we're leading a work stream, the chiplets modularity for HPC and artificial intelligence. If you're interested in this, I say join us. We meet bi-weekly, Tuesdays, 9 a.m. Pacific time. But basically, we're trying to understand if you have a chiplet and I have a chiplet, how do we put them together on the same interposer? It sounds easy, the technology is there, but there are many challenges to address. And we're trying to address them with a group of volunteers, which is actually very interesting as well. So based on all these projects that we have and the conversations we have with the industry, we come up with a recipe for hardware specialization enabled by chiplets modularity, and we have 6 steps to make this happen. The focus of this, we have our ingredients is that if we go to a chiplets marketplace, we need to buy 4 chiplets and 1 interposer. And with those chiplets and the interposer, we are going to be able to build 3 different optimal systems in package. And in this case, we're using artificial intelligence to create the example. So step 0, we want to identify what specialized hardware do we need to build an accelerator for artificial intelligence. So we use Gemini, which is a project that's an open source AI accelerator coming from UC Berkeley that is based on a spatial array similar to the TPU, to the Google's TPU. And from that accelerator, we come up with our step 1, the chipletization of hardware acceleration. So we have a systolic array chiplet that is basically a grid of processing elements. Like the basic is multiply accumulation units. Then we have a scratchpad chiplet that is going to be SRAM based, and then we have an accumulator chiplet. And we're gonna, like in an ideal world, they all exist in the chiplets marketplace. In step 2, we design our interposer, and I don't know if this looks familiar to what we saw earlier today, but basically we define that we need a a two-dimensional grid that with n-by-n chiplets, because this helps us with scalability. We need more chiplets, we increase the number of columns or the number of rows. We need a networking package. We think that the networking package needs to be super, super simple. Closer to the physical interface that we're going to use more than complex protocols. Has to be lightweight, and we want this to have a minimum transmission latency, because when we connect this to chiplets, we want the application to see as if the chiplets were on the same chip. If all the blocks were on the same chip versus a chiplet versus different chips. We advocate that for these particular accelerators, we don't need cache coherency. These accelerators in general don't need to participate from the cache coherence mechanisms that we have for CPUs and GPUs, because this is not general purpose computing. So instead of that, we use message passing similar to MPI. And then this will work because we assume that the data flow is regular and predictable. The chiplets are going to communicate with the neighbors versus communicating, from one corner to the other corner of the two-dimensional array. Okay, so the step 3 is defining our architecture, and this is the architecture we define for an artificial intelligence accelerator. So in the left, we're going to have a lot of SRAM buffers to handle all the input and outputs. On the top, we're going to have more SRAM buffers to handle all the train parameters. In the middle, we're going to have the systolic array accelerators. And on the bottom, we're going to have the accumulator chiplets that are going to aggregate all the information coming from the processing elements. This K by K array of systolic arrays is going to act like if it were a larger systolic array, and I'm going to decide how many of those will I need for my applications. And then finally, I need an I/O chiplet that allows me to communicate to and from the host. In step 4, so we do some math, and we need to define the chiplets area and parameters. So I don't get confused by that figure, but basically what this is telling us is that if the bump pitch, the bump pitch is basically the distance between the connections that we have in the chiplets, is larger than 40 micrometers, we need to use standard interfaces. If you have heard about chiplets, basically we have UCIe and a bunch of wires. These standard interfaces are running at very high frequency to give you the bandwidth that you need. But they need serialization, and they require more power and latency. So that's, when we look at it from the energy perspective, it's not necessarily what we want. But if the bump pitch is less than 20 micrometers, what we can argue that we can use just simple oversized buffers, and we have enough data lengths to reach the bandwidth that you need for these particular AI accelerators. The bump pitch of 20 micrometers is in the horizon, is what they are planning. So we're going to see, we're confident that we're going to see that kind of bump pitches in the near future. Okay, so with all these that we have done, we know we know the chiplets that we need, and we also know the characteristics of the chiplets. We run synthesis and place. We have the logic, we have the Verilog for all these. We run synthesis and place and route in different technologies, sub 20 nanometers, sub 10 nanometers, sub 5 nanometers. We know how much can we put, how much processing elements, how much memory can we put in this area. And then the final step, or not the final, the almost final step is profiling AI algorithms, right? So, and that is when we have to do this co-design loop where we need to talk with algorithms, with applications, with software people, and then that's not as easy as it sounds because we don't talk the same language and we don't care about the same things. But basically, for this particular example, we want to find the optimal size of systolic array and the optimal scratchpad capacity for this. So we run experiments, and the conclusions that we get is most CNNs require a squared systolic array of 256 by 256. Beyond that is completely inefficient, so you don't have to go larger than that. Some of them require DRAM, some of them do not need DRAM. There are some particular machine learning architectures that benefit from tall and skinny systolic arrays versus the square that is kind of standard in every single hardware accelerator. And it definitely needs DRAM. And then we have the transformer that is our example for artificial intelligence. So this one is tricky, is very tricky, and we can talk about it, but we're gonna, for now, say that a large systolic array of 512 by 512 is the maximum we wanna go with this. Something larger is going to be basically, it's gonna hit the memory wall. We need another chiplet, we need embeddings. That is something that we had not seen that often on the previous machine learning algorithms, and we need DRAM I/O. That's the two new chiplets that we had not considered, and we got these out of our profiling exercise. Okay, so the final step is we put all together. So if we use a sub-20 nanometers system in package together, and I say sub-20 nanometers because I cannot tell the technology, because of NDAs, I cannot tell the technology we were using for these evaluations. We find that for CNN, we need, this is the size of the systolic array, and then this is the number of chiplets I will need, the systolic array chiplets I'll need. So you see that for the transformers, we need 64. For deep speech, we need only 8. The memory we need, the bandwidth. And then I look into the interposer size. And what I see is that while CNN and deep speech are on the border of the largest interposer I can build today, for the transformer, this interposer is too large. I cannot build this today. This interposer is not possible. So we have to go and look into sub-10 and sub-5 nanometers technologies for if we want to target artificial intelligence. And that's one of the biggest questions we had. Why don't we use 130 nanometers for our prototyping? Well, it's not going to work. And then we see that if you see the transformer, then we are back into what is possible for the interposer, 38 by 38 millimeters. And then if we want to target AI applications, we need to go for a sub-10 nanometer, sub-5 nanometer technology, which is the most advanced nodes available today. Okay, so we evaluate our approach, and we say, of course, the obvious response is that you see here the normalized latency for 3 examples. And we get better performance because we optimize for performance, so there's no surprise there, right? But then when we look at the energy consumption, it is actually surprising that if we use the most advanced node, the energy consumption triggers. And that's because the most advanced node is enabled to run at very high frequencies. It's actually doubling the frequency, but it doesn't reduce the latency enough to counteract. So if we were optimizing for energy consumption, we wouldn't go to the sub-5 nanometers. We would stay in the sub-10 nanometers to get the maximum energy and latency efficiency. So just to conclude this part of the talk, and actually the whole talk is, I would say we don't need to fit our specialization if we're capable of leveraging the modularity of chiplets. So I show you how we can, with 4 chiplets and 1 interposer, we can design 4 highly specialized system in package for artificial intelligence without absorbing all the non-recurrent engineering costs, which is very expensive. It's going to be a very fast deployment because all the chiplets are all working already. All that you have to do is put them together. All that you have to do is an oversimplification, but it's a lot simpler than having to design all these chiplets and then test the whole, and then design again an entire chiplet just because you want to change a couple of things. We demonstrated that we can have more than 100 times less latency than using a square systolic array that is the baseline that everyone uses. And we can have more than 10 times better energy consumption. So it is a possibility to at least delay the energy crisis. So the final thoughts here is we cannot design a chiplet for an application. I cannot tell you, you cannot tell me, oh, I want to design a chiplet for a transformer, for example. That's not gonna work, it's too expensive. But I can identify the key kernels that I need for scientific computing or artificial intelligence and map those kernels to a chiplet. And then we have, and then if we identify those kernels, we're gonna have the ability to have a specialized hardware for many different HPC applications. That is what we care about, and artificial intelligence that we just discussed. Just to finish this talk, so there are many ways to address, or there are many possible ways to address the beyond more era of computing. So we can go in the X direction, where we look into new architectures and packaging. That is all that we talked about, where we know that there is plenty of space at the top. And to do that, we have to look into software algorithms and hardware architectures need to work together to enable this specialization and to enable this ecosystem for really targeted hardware. But there is also these new devices and materials. And in the past, when we looked into new devices and materials, we were looking into the replacement for CMOS. And no one has been successful in replacing CMOS because CMOS is actually really good for what it does. It's amazing. Why would we replace it? But with this new paradigm of specialization, modularity, heterogeneity, what we can think about is all these new devices and materials are more like a complement for CMOS. So we can have a completely, like our HPC systems could be a combination of neuromorphic computing, quantum computing, and superconducting computing all together to solve the next generation of scientific problems. So with this, I wanted to just give you a hint of what we're doing for quantum computing, which is and this is something interesting because when I think about quantum computing, everyone is thinking, oh, this is the cutest thing in the world, the shiniest thing in the world. But the reality about quantum computing is that this is how a quantum computing really looks like. So we have the cryogenic refrigerator, where we host the quantum processing unit. But the reality is that quantum processing unit is not going to do anything without all those wires coming out connected to all these room temperature electronics, which involves waveform generators, data converters, control and data flow processors. And what we know is that this not necessarily beautiful quantum processor is simply not scalable. To do real applications, we need to look into 10,000 qubits, billions of qubits when we look into virtual and quantum error correction. So it's just, we know that it's not gonna work. So the solution we're working on is what do we need to do to put all these quantum control inside the cryogenic refrigerator? And what we're doing is we're dissecting block by block around the transmode qubit and evaluating how, with different strategies, how do we put it into the cryogenic refrigerator. In particular, we are using superconducting classical computing to do this, and machine learning. So it's a combination of neuromorphic computing, machine learning, superconducting computing. And then this is just another example of what we talked at the beginning, is another example of a specialization. And with this, I want to finish here. Thank you all for your attention, and yeah, happy to talk.
Thank you very much.